Hello everyone. Today we are going to discuss about vector atomic model. Two of the very characteristic features of vector atomic model are spatial quantization and spin of electrons. Spatial quantization means all the vectors associated with the electron in an atom must be quantized both in magnitude as well as direction. The direction of the external magnetic field is considered as the direction of the reference for the quantization. The spin of electron means the spin of an electron is an intrinsic fundamental form of angular momentum possessed by the electron entirely independent of its spatial movement or orbital motion around the nucleus. Around the nucleus. Let's see spatial quantization in much detail. We know that in classical mechanics, when we have a spinning body, it can have any direction for its spin. That means when electrons, so yeah, atoms or electrons orbital angular momentum defined by L according to classical mechanics will have arbitrary direction. But according to quantum mechanical postulates, atom or electrons orbital angular momentum won't have any arbitrary direction, but the direction to which this L will point is quantized. That means it would have some specific values for the allowed values of orientations, and the orbital angular momentum L, capital L, is given by this formula where small l refers to the orbital quantum number. And so yeah, one thing that I should talk about is that spatial quantization the is not only present when the magnetic field is given, but it is physically manifested when the magnetic field is visible or is given. What I mean is spatial quantization always happens, alright? Sorry for that. Spatial quantization always happens, but it is manifested only when an external magnetic field is given. What I mean is that whenever we give whenever we pass magnetic field through an atom, then that magnetic field direction would act as a reference direction, and along that reference direction the spatial quantization would happen. And in that process it would manifest by the splitting of spectral lines and by Zeeman effect. That spatial quantization phenomenon actually happens inside the atom. So this is how we find out that such kind of phenomenon happens. Only so that means when we can only find out that phenomenon when we apply a magnetic field to the atom. So whenever, let's suppose we apply a magnetic field, then that the direction of that magnetic field would act as the reference axis, and we would get a quantized number for the reduced Planck constant. That means this would give us the direction, not the direction itself, but the allowed values. This ml here stand for magnetic quantum number, and it has values from minus L to plus L. L, if you don't remember, is the orbital quantum number, and ml would have only 2l plus 1 values, which are allowed values. If you want to find out the angular directions which are allowed, you can find out it by using this formula. cos phi, cos theta equals Lg by L, and it is given by ml by root under L plus 1. Defining characters of vector atomic model also includes a spin of electron. Every electron in the universe possesses a fixed immutable total spin angular quantum number given by S, where small s is the spin yes sorry yes the small s stand for spin of each electron, and capital S stand for the spin of whole atom, and this spin of whole atom is given by this formula. And whenever we don't have any magnetic field, the value of S for an electron, for a single electron atom, would be always equal to root under 3 by 4h. Like in the orbital angular momentum, when the electron is exposed in the magnetic field, then another quantum number would come into the scene, and that is ms, which is a spin magnetic quantum number, and it restricts the values of electron in either plus 1, plus half, or minus half. That means whenever we apply a magnetic field to a electron, to an atom, and if that atom is a one electron system, then it would have only two possible directions in reference to the magnetic axis, and they are plus half and minus half. Plus half, if ms is equals to plus half, then it is said to be spin up, and that means that the component of spin angular momentum is aligned parallel to the positive direction of the external magnetic field. That means the direction of the spin points in the same direction to where the external magnetic field points. Similarly, if the spin if the ms is equals to minus half, then that would be called as a spin down, and that means that the spin vector would point in the opposite direction, anti-parallel direction to the external magnetic field. Because the electron is moving negative charge, this intrinsic angular momentum would create an intrinsic magnetic property called the spin magnetic dipole moment. We are already familiar with the phenomena because we have seen it in the multiple cases. Whenever we have an electron moving around, then it would create its own magnetic property, it not magnetic property but magnetic field, and that intrinsic magnetic property of creating that magnetic field would result or would be called as the spin magnetic dipole moment. This magnetic moment interact with the external magnetic external magnetic field. Now we already know that there is external magnetic field too, and when electron revolve around, and since electron is also a charge, it will create its own intrinsic magnetic field. And this intrinsic magnetic field and external magnetic field would would interact with each other such that this would result into the splitting of the spectral lines that we are familiar with, the term that we call as fine structure. Okay, so that turns out to be the absolute reason behind why the fine structure is seen, or why does the splitting of spectral lines happens. So the real reason for fine structures turns out to be described by Becker atomic model is due to the interaction between the spin orbit magnetic spin orbit quantization, okay, or we can say spin orbit interaction. So what is spin orbit interaction or spin orbit coupling? So how can we define it? So we can define it as the following statement. This is a relativistic quantum phenomena where the electron's intrinsic spin created by movement of it around the nucleus and the external magnetic field applied to the atom interact with each other, okay, that the phenomenon that is resulted from these interaction of the two magnetic fields is called a spin orbit coupling. Now remember, we are talking about, now this is true for all the atoms consisting from one to large number of electrons. But we are now here talking about only one electron system, because when we see one electron system it is much easier to understand, okay. But whenever we have large number of electrons or multi-electron models, multi-electron atoms, a spin orbit coupling won't be so easy, because as you see, whenever we have only one electron system, the atomic or the quantities that hold account for the orbital quantum number, spin quantum number would be equal to the spin quantum number of the electron. But if there are larger number of electrons, then the larger number of electrons would interact in such a way that we have to calculate the mean or the average of the spin sorry yes spin quantum number, and that would be the spin of the atom, okay. So it turns out that for multi-atomic models, multi-electron models, multi-electron atom, we have to consider the case of different kind of coupling, different types of coupling. Those type of coupling are Russell-Sanders coupling, wait a second, yeah, Russell-Sanders coupling and JJ coupling. Russell-Sanders coupling occurs in light atoms. That means whenever we have whenever we have atoms which has low atomic number, Z Z smaller than 30, in such kind of in such kind of light atoms, Z, that is the nuclear charge, is small, okay, and due to that the spin orbit interaction is extremely weak, and electrostatic repulsion between the valence electron would be dominant. As a result, the electrostatic repulsion is strong, and and the individual orbital angular momenta L1 L2 would couple together strongly to form a single massive total orbital angular momentum given by capital L. And capital L can be mathematically called to be summation of Li. Simultaneously, the individual spin angular momenta S1, S2 up to Sn interact via spin exchange forces and couple together strongly to form a single total spin angular momentum given by S equals summation of Si. And to find out the total angular momentum, we would add these two quantities, and such that we would get the formula J equals L plus S. Okay, if you see JJ coupling, it happens in the heavy atoms when atomic number is greater than or equals to 80. such as lead, thallium, or mercury. The strength of internal magnetic field experienced by an electron is directly proportional to Z to the power 4. And here, in heavy elements, the nucleus has a massive positive charge, pulling the internal electrons into extremely fast and high relativistic speeds. The spin-orbit interaction becomes so overwhelmingly powerful that it completely overrules and shatters the electrostatic repulsion, holding L and S together. That's why we would get that each of the electron or the yeah so the individual total angular momentum given by Ji is given by the individual sum of the orbital quantum number and the spin quantum number of each electron. So to find out the total angular momentum you of the total of the whole atom, we would just sum each of the angular momentum of electron. So you can see we are talking about two kind of forces here. Two kind of forces are involved in coupling. First one is spin orbit forces or spin orbit coupling, and second one is electrostatic. Wait a second. Yeah, electrostatic repulsion. That means if you see the spin orbit interaction is a physical phenomenon, you would see two kind of forces here. First one is residual electrostatic repulsion. Second one is spin orbit interaction. Whenever the residual electrostatic repulsion is greater, then in such kind of atoms, LS coupling or Russell-Sanders coupling is dominant. Similarly, the atoms with the high atomic numbers has high nuclear charge, and as a result, the spin-orbit interaction would be much dominant than the residual electrostatic repulsion. As a result, in larger atoms or large number of electrons, such kind of atoms would have a J coupling. Okay, so these are the types of coupling. Now, you might want to know how does this spin orbit interaction as a physical phenomenon happens. Now it is beyond our scope of class, but I just want to discuss it. Okay, so if you want to see, you can see it, otherwise you can skip it. It is not in your syllabus. So we can understand a spin orbit interaction as the following in the following way. Relativistic coordinate transform. In the standard laboratory frame of reference, we consider nucleus to be at rest. Because nucleus has larger at mass than the electron, so we consider nucleus to be stable and stationary, and electron revolve around the nucleus. Yes, electron around the nucleus. Sorry for that. But if we see it from another frame of reference, we can consider electron to be at rest and nucleus to be revolving around the electron. If you see in that way, then the moving positive charge generates a massive internal magnetic field at the position of electron. And that positive charge can be given by Biot-Savart law. which is given by this expression right here. Here E is the nuclear electric field and V is the electron velocity. Actually, not the electron velocity in this case. If we consider uh, nucleus to be, yeah, we can think of it's big. Okay, we are right now thinking about nucleus being revolving around the electron, but if it was in the case of electron revolving around the nucleus, we would consider this expression where V is the electron velocity, me is the electron mass, and c is the speed of light. Since the central electric field expression is given by this, we can consider that the B is directly proportional to the orbital angular momentum. The electron possesses an intrinsic spin, as we already know, and this value here suggests that it has an orbital angular momentum too. So, because of this intrinsic spin, it has its intrinsic spin magnetic dipole moment too. And when a magnetic dipole mu s is placed inside the magnetic field, due to the interaction between the magnetic dipole and the magnetic field, it presses, given by Thomas precession, and the interaction energy in between this system is given by this formula. If we substitute the value of mu s and b, we would get fundamental spin orbit interaction Hamiltonian given by this formula, where you can see this L times S is the is holding account of spin orbit coupling, and this uh, what is it called? It is xi, I think it is xi, yeah. Xi r is a of function also known as spin orbit coupling function, and this ls is called the coupling, and it is the ultimate reason for the fine structure. So in a vector atomic model, the total angular momentum vector is given by L times S is equals to, sorry, J is equals to L plus S. Now L times S is given by 1 by 2 J squared minus L squared minus S squared, and it follows from the cosine law in the quantum mechanics. You can think of it. You can refer to the quantum mechanics book for this. Substituting the operator's quantum mechanical eigenvalues, this yields this function. It is necessarily the Hamiltonian, and it accounts for the change in the change in the interaction energy, and this is called zeta by 2 of this factor. And because the electron spin is s equals half, orbital state L is always greater than 0, so the total angular momentum quantum number J is placed exactly into two orientations. And again, remember that this is in the case where the magnetic field is present, external magnetic field is present. In that case, the total angular momentum quantum number splits into exactly two orientations, two orientation states, parallel orientation as well as and anti-parallel alignment. I have already discussed it previously, if you remember. Uh, so okay, and then we will get J equals L plus half or J equals L minus half in parallel and anti-parallel alignment respectively. So a single energy state defined by a principal quantum number n and orbital quantum number L which would produce a single spectral line in an older atomic model is physically split into two distinct sublevels depending on whether the electron spin magnetic moment is aligned with or against the internal magnetic field of its orbit. And when an atom consists more than one electron, I have already, okay, so Yes, this is the reason for defined structure. And I have already said that if the atom contains more than one electron, then there will be two distinct pathways for multi-electron combination to happen in terms of coupling, and that would be governed entirely by two forces. First one is residual electrostatic repulsion, and second one is relativistic spin orbit interaction. I have already discussed these things, and this coupling, Russell-Saunders coupling and JJ coupling, are actually important from the perspective of examinations. So this is it. Thank you so much for watching this.